Okay, so to define this, right, we're going to say that f of x, our function, is a, and this time what makes an exponential function different from everything we've done is that the exponent is the variable, a to the x. We're going to say that a has to be a number above 0. We call a the base. And then x is going to be any real number. Okay. And I guess we'll say one more little criteria on this, and that is simply that we'll say that a can't be 0, or 1, I mean. And why would that make sense to have a not be 1? Why would 1 be a poor choice for a function a? 1 to the power is 1, right? So that would not be a smart choice. It would not be a very interesting graph to have at all. So we won't do that. So some examples we could talk about, pretty common examples, would be like f of x is 2 to the x, or f of x is 1/2 to the x. Okay, well, so there's what an exponential function is. Now, you know, the graph of a function certainly tells us a lot about the functions, and we're going to look at that next. So to kind of explore this, let's just go ahead and sketch the graph of f of x is 2 to the x. And yeah, let's do this by making this a table of values to graph. Kind of like you did way back in 7th grade, 6th grade, I don't know. You know, when we plot these points, we're looking for a pattern. So let's just start maybe at, let's say, -3. So let's see, f of x would be 2 to the -3 power. So what's that going to equal? Well, first off, we know to make that positive, it goes to the bottom, right? So that's 1/2 cubed. It'd be an 1/8, right, an 8. And let's just go through some values. And if we do -2, that would be 2 to the -2 second power. 1/2 squared, that's what number? 1/4. -1 is 2 to the -1, so that's going to be 1/2. 0. Anything to 0 power is 1. It's always an interesting concept. First would be 2 to the first. 2 squared. 3. Alright, so again, that's to give us kind of a pattern to look at, right? Because we can extend that pattern to see what all we can conclude about this graph. Well, I got some very small values I'm going to have to plot. So I can squeeze these in. So we said negative 3, it's down to an 8. So that's really close to the axis. And negative 2 to 4 is not a whole lot bigger. It's a half at negative 1. Function gets up to 1 at 0. 1 is at 2. 2 is up to 4 and jumps way up. 3 goes way up to 8. So we get a pattern like that, and then if we connect that with some kind of a smooth curve, right, we get a pattern like this. And then if I extrapolate that and try to even extend that further, let's see, so this line comes down like this. This line comes up like this. And there's our graph. So let's do a graph summary. What can we say about this graph? So what interesting features does this graph have?
There's an asymptote.
Right, so there is a horizontal asymptote. Well, in fact, let's start the domain. Let's just do some of our standard stuff. What's the domain of this graph? The graph extends and covers all the x values. So there's no x values without a point. That's all real numbers. Negative infinity to infinity. But the range is not that way, is it? This graph gets infinitely close to the x-axis, never gets to there. So it starts at 0 and goes to infinity. We said it has a horizontal asymptote. And that is at, what's the equation of this line? Y equals 0. That's the x-axis. And there's no x-intercept. Never crosses the x-axis. But where's the y-intercept at? Yeah. So that'd be 0, 1 would be the point. Yeah, so that's kind of our summary. So all exponential functions have that basic shape, that basic graph. Now, if I adjust the base, it fluctuates some, but it actually, if the base is less than 1, there's a big fluctuation. I want to look at that graph next. To compare that to. Yeah, so remember we said we're going to have A has to be positive, but if it's between 0 and 1, there's another interesting thing that happens. So let's look at that. Let's explore the graph. This time I'm going to do f of x. Let's just do a half. That's just pretty easy. A half to the x. So a half to the x this time. Let's see. So same idea. Let's just plot some points and look what the graph is doing. And so here's x, f of x. Let's just start at negative 2, just to make it a little quicker. So if I have a half to the negative 2 power, well, how do I do that? When I have a fraction to a power, right, I can take both the top and the bottom to that power. That's like 1 to negative 2 over 2 to negative 2, right? Now, what do I do here? Yeah, because of the negatives, right, to make them positive, the bottom goes to the top, and the top goes to the bottom. So that's the same as having 2 squared over 1 squared. And the value of that is in fact 4. Okay, so that's a lot different now than last time. Because as we moved to left last time, right, it dropped way down. So a negative 1 would be a half to the negative 1 power. Right? And again, same thing. 1 to negative 1 over 2 to negative 1. When I switch that, I get that equal to just 2. If I do 0, what happens? Oh, that's easy, right? Always, no matter what it is 1. If I do positive 1, that's a half. And if I do positive 2, that would be a half squared root of 4th, right? Yeah. So now we take, again, if we sketch this out, so negative 2, in fact, then is up at 4. So we got a dot there. Negative 1 is at 2. 0 is 1. Then it's a half and a fourth. So you get a graph like this. And if you can imagine, if I connect this, it's going to continue to get lower, lower, lower. It's going to go up like this. Plus u. Now, if we look at our graph summary, we get a lot of the same things as last time. So my domain is what? Sure, domain is the same. The range, well, in fact, that's the same, 0 to infinity, yeah. The horizontal asymptote, same. And let's see, oh, the y-intercept. That is, yeah, 0, 1 again. So that's the same. So what's different about the graphs? Yeah, in fact, if we think about it this way, this one is decreasing, right? So this one's going down, decreasing, but the one we did here was increasing. Yeah, so we can make that statement as well. So we'll kind of summarize that. So if on C, so if we have the A, the base, is greater than 1, like the first one we did, then the graph is increasing. So the graph would go increasing and go up like this. But if the base, the A, is between 0 and 1, so basically it's a fraction, then the graph is decreasing. So one of the things then you'll be doing is some translations, and then we're in this lesson with solving some equations. But the translations are a lot like other graphs. In fact, they're very much like it. So it's not a lot new on this. So let's call this Part 3, translations. Stretching and reflections. Okay, so yeah, let's just describe some. So describe each translation. So first one, 2 to the x minus 2 power. So you just ask yourself, if I subtract from the x, what's my translation? Which way will it move that? Subtracting from the x moves it right. Right. So this is simply just, it moves the whole graph right too. So remember, if we subtract from the x is right, add to the x is left. And the x is what's critical on this. If I take and, so number 2, f of x is 2x minus 4. If I subtract 4 from the 2x, what's that do? Yeah, so that's like taking the whole graph, 4 from each point. Right, so that's down 4. Now, remember that if I do move it down, it changes the horizontal asymptote. So now the horizontal asymptote is at x equals negative 4. Not x equals, y equals negative 4. It moves the whole thing down. If I would add, it moves it up. F of x equals 2 to the negative x. What happens if I take the x times the negative? What's that going to do? Reflect it where? Yeah, so think of it this way. I'm taking all the x values and moving them to the other side, right? It reflects it across the y-axis. And if I take the negative and put it in front of the 2, so f of x is negative 2 to the x. What does that do? Reflect it across the x-axis. Okay. And then one more thing on translations. This should be like a B. If as the a value changes, you get you basically get a stretch or a shrink, and so B. Changing the a value. And again, we have the form of f of x is a to the x. When we change the a value, we're changing that base. So, think about it this way. So as a becomes larger, that would be a vertical stretch. It makes it go up faster, which should be pretty obvious. But if I have a bigger value, I'm taking the power to, it's going to make it go up a lot faster. We call that a vertical stretch. And then as a becomes smaller, that would be essentially a vertical shrink. Okay, we're in today talking about solving some different types of exponential equations. Now, we'll be somewhat limited to today the type we can solve because we have to actually look at logarithms for the other type. But I think I'm ready for number 4. Your book calls these type 1. The author calls this type 1, which is fine. So we're going to look at solving type 1 exponential equations. Okay, so you're going to solve these. One of the properties of exponents says that to use that a to the b equals a to the c if and only if b equals c. Okay, that should make sense. It's pretty obvious. But if I have two of the same base equal to each other, then the exponents must be equal, right? And so that's one pretty obvious one to use. If and only if, of course, means that you can go both ways. That if this is true, and if b equals c, then this is also true. So you can go both ways on that, an if and only if statement. That's why we often say it like that. So, some examples. Well, first one, 25 to the x is 125. Well, initially this is maybe not quite as obvious because I don't have the same base on these. But, of course, you ask yourself, can I write these as the same base? So let's see. We know that 25, let's see, how can I rewrite that? Well, what base would fit both 25 and 125? 5, right? So 25 is actually 5 squared, and that would be up to the x power. So I'm rewriting with the same base. $125 would be 5 cubed, right? Well, it's kind of awkward how I wrote this 5 squared to the x power, but if I have a power to power, what do I do with those two values? I multiply, right? So that means that that's the same as having 5 to 2x is 5 cubed. And of course, now I can apply this property here that says if I have two bases exponents are equal, then that means that b must equal c. In other words, then 2x must equal 3, so x has to be 3 halves. Okay? So all these types of equations, we'll be able to write these essentially today with the same base. And once we develop the idea of logarithms, then we have another tool we can use. But right now that tool doesn't exist. My second example, 5 to 2x plus 1 equals 25. So my first step would be to do what? So write that 25 as 5 squared. So it means that 2x plus 1 has to equal 2. So 2x is 1, or x is 1/2. Okay, 3 is this looks a little different, but it's about the same. This one I have a third to the x equals 81. So what base can I write this one as have the same base? Yeah, 81, I'm thinking 81 base 3, because 3 to the, yeah, 4. So I'm going to write both these as base 3. So that was, so 1/3 in fact is 3 to the -1 power. And that's still to the x. So I can write a third as 3 to the -1. And then 81 is 3 to the 4. Yeah. So yeah, so power to power multiplies. So that's like 3 to the -x is 3 to the 4th. Okay, so now -x equals 4, and x is -4. Okay, questions on those? Okay, so what I have left on this section, what time is it? Is some application questions. I guess we can start this next one. We have a little time yet.
We still have to look at our test.
Okay, test. We can start this for a few minutes, and we'll finish up tomorrow. No doubt you have seen these applications of interest, but Butler almost always has one or both these on the final. So they certainly have liked it quite a bit. I'm ready for section 4. 5. Yes, 5. And the first one is compound interest. And most likely you've done this before. Now, the formula for compound interest, A is P times 1 plus R over N to the NT. This will be on the formula sheet. Okay, so that's on the formula sheet, so you will not have to have that memorized, but you will need to know what each of these variables stands for. Okay, so let's run through that. A stands for, as we call it, the amount, and it's after time t. And usually with interest, t is in years. Now, often if we do some other type of growth, like population growth or things like that, it may not be years, but for interest, it's almost always years. P stands for principal. Remember, that's the starting amount.
Pretty sure that's one.
Is correct. And that's time equals 0. So time is 0. That's how much we start with. The other principle is like a principle in biology, which is LE, but this is principle, same as the principle of the building. R is interest rate. Make sure you write that as a decimal, because sometimes students are on tests and they forget to change it to a decimal and they get this huge number. But make sure you write that as a decimal. The N stands for number of times compounded per year. That's usually a per year. And interest, it should be per year. And T will be time. I think it's going to be years. Right, and this typically is just a matter of plugging the values into the formula and then correctly typing those into your calculator. And I encourage you to practice both those because I've seen mistakes on both. Let me squeeze one quick example in and we'll stop for today. So we're going to invest with $1,000 is invested at an annual rate of 4%, compounded quarterly So how much is in the account after 10 years? So like I said, these questions come down to typically just plugging the numbers in. A equals, the principal would be 1,000. 1 plus R, 0.04 over N. So quarterly, right, that means 4 times a year. And then it's 4 times T, which is 10. So like I said, it often comes down to can I correctly type it in, and if you use a TI calculator, you certainly can do this all in one step. If I can show both these, so I can squeeze this in. So I'm going to have 1,000, 1 plus parentheses 0.04 divided by 4, caret, and 40. If you take the 4 times the 10, make sure you put that in parentheses as well. 1488.86. So after 10 years, you have that much in the account. Of course, if you want to put money in the account right now, the interest is way less than 1/10%. So that's actually be very good interest compared to what you get today.